Nuclear reactor. In this video, we're going to learn about the nuclear reactor. Nuclear reactors are the modern-day devices extensively used for power generation as the traditional fossil fuels, like coal, are at the breach of extinction. A nuclear reactor is the source of intense heat which is in turn used for generation of power in nuclear power stations. Its mechanism is similar to that of a furnace in a steam generator. The steam is used to drive the turbines of the electric generator system. A nuclear reactor consists of three crucial components: fuel elements, moderator, and control rods. Fuel elements come usually in the shape of thin rods of about 1 centimeter in diameter and contain fissionable nuclei like uranium-235 or uranium-238. These rods vary in number according to the size of the reactor. In large power reactors, thousands of fuel elements are placed close to each other. This region where these fuel elements are placed is called the reactor core. These fuel elements are normally immersed in water, which acts as a moderator. The objective of a moderator is to slow down the energy neutrons in a nuclear reactor, which are produced during the nuclear fission process by the fuel elements. Thermal neutrons, which are the neutrons with energy of about 0.04 electron volts, are capable of producing fission reaction with uranium-235. During the fission reaction process, new neutrons are given out, which have energies of about 1 MeV. This is 1 mega electron volts. These neutrons typically escape from participating in another fission process, as they are accompanied by enormous energy release. In fact, the probability of these neutrons produce another fission reaction is 500 times less than that compared to a thermal neutron. This is where a moderator is extremely useful. Moderators have the capability to slow down, or in other words, moderate, the speeds of these high-energy neutrons so that they can in turn be used for a chain reaction to trigger multiple fission reactions of other uranium-235 nuclei. Commonly, ordinary or heavy water is used as a moderator in nuclear reactors because of the deuterons present in them, which are capable of slowing down the neutron speed. Water molecules in the moderator are useful in slowing down the high-energy neutrons, which leave the fuel element after nuclear fission. These high-energy neutrons collide with water molecules, thereby losing out on some energy with every collision and therefore slowing down substantially. A new fission reaction can now be triggered using this slow neutron by striking it with a fuel element. The third and most prominent part of a nuclear reactor are the control rods. In order to get a steady output of energy from the nuclear reactor, every single fission reaction should trigger another fission reaction and ensure the availability of spare neutrons released to trigger the chain reactions. By controlling the number of spare neutrons available at any given time, the rate of nuclear fission chain reactions can be controlled. This control on the fission reaction can be maintained using control rods. The main function of the control rods is to absorb any excess or spare neutron in the moderator in order to prevent any further fission reactions. Usually, such control rods are made of boron or cadmium. To increase the rate of fission reactions, these rods can be removed from the moderator. A steady output of energy can thus be maintained by inserting or removing the control rods in the nuclear reactor. Now that we know the components of a nuclear reactor, let's understand the working of a nuclear reactor. It's usually enclosed in a shield made of thick concrete walls. It consists of a reactor core, pump, and heat exchanger. The reactor core and pump are placed in contact with the water, which is usually the heat exchanger in these reactors. Due to the enormous amount of heat released during the fusion reaction, the surrounding water gets heated up and changes to steam, which is in turn used to turn the turbines. So, huge heat energy gets converted into electrical energy. Water is continuously flown in and out of the nuclear reactor using the pump. So, a nuclear reactor successfully generates nuclear energy from fission reactions.
The process of creating electricity using nuclear power begins with the splitting of uranium atoms in the reactor. This process, called fission, produces heat. In a boiling water reactor, the water surrounding the nuclear fuel is turned directly into steam in the reactor vessel. The steam is then transferred by pipes to the turbines. The spinning turbines drive the electric generator to produce electricity. After the energy from the steam is used to spin the turbines, it is drawn into a condenser where it is cooled and condensed back into water and pumped back to the reactor to be boiled into steam again.
Advancements in technology include improvements in reactor designs, components and performance, and sophisticated safety, security, and waste reprocessing systems. Each new generation of reactor is more efficient, cheaper, and safer. Nuclear plants use a series of physical barriers to contain radioactive material. Everything is encased. In today's water-cooled reactors, the first barrier is the fuel itself. Solid ceramic uranium pellets. Most of the radioactive byproducts of the fission process remain in the pellets, which are sealed in zirconium alloy rods. These fuel rods are in a large steel reactor vessel with walls 8 inches thick. The vessel is surrounded by 3 feet of concrete shielding. At most plants, a leak-tight steel liner covers the inside of the containment building, which is itself a massive, reinforced concrete structure with walls 4 feet thick. So, where does nuclear power fit in today's energy mix?
are Rbmk 1000 designs, which are graphite moderated and light water cooled. The core is kept in a helium-nitrogen environment, as high-temperature graphite can combust in air. Some Rbmk reactors have partial containment structures, but they notoriously lack full containment. Chernobyl reactor number 4 in Ukraine, which suffered the worst nuclear accident in history, was an Rbmk 1000 reactor. Rbmk reactors still in operation are considered by many outside experts to pose continued safety concerns, in large part because they lack full containment structures.
Over the last quarter of the century, several generations have changed not only in society, but also in reactor engineering. New Russian power units now are fitted with Generation 3+ water-water reactors. Reactors of this type can be called safest, without exaggeration, because there has not been a single serious operational event over the entire period of VVER reactors' operation. Simple arithmetic says that over time of their operation worldwide, the water-water reactors have accounted for a total of more than 1,000 years of fail-free operation. In the reactor, nuclear fuel is encased in zirconium tubes or fuel rods. They constitute the reactor core. When absorber rods are withdrawn from the core, neutron flux increases and self-sustained chain fission reaction starts. Uranium nuclei fission to release a vast amount of energy which heats up the fuel rods. Nuclear power plants with VVER reactors employ a two-loop arrangement. Ordinary water, cleaned from all admixtures, circulates through the reactor. When passing through the core and washing over the fuel rods, it is heated up to 320 degrees Celsius. To keep it in liquid state, it has to be under a pressure of 160 atmospheres. Then, heated water gets into the steam generator and transfers its heat to secondary water, and afterwards is pumped back to the reactor. Then, everything happens at a conventional power plant. Secondary water is turned into steam in the steam generator. Steam rotates the turbine, and the turbine moves the electric generator. It is the generator that produces the electric current. The reactor and steam generator are inside a leak-tight concrete shielding. In the steam generator, primary water does not physically contact with secondary water which goes to the turbine. This arrangement and location of the reactor and steam generator exclude radioactive substances getting beyond the plant's reactor hull. At Russian nuclear power plants, costs of safety systems amount to 40% of the total cost of the plant. A sizable share is spent for automation, power unit design, and safety systems. The VVER reactor safety is based on the defense in-depth principle, which is the use of a system of 4 physical barriers preventing releases of radioactive substances. The first barrier is the strength of the uranium fuel pellets. After so-called sintering in a furnace of a temperature of more than 1200 degrees Celsius for one day, the pellets acquire high-strength properties of ceramics and do not break under high temperatures. Pellets are placed in zirconium tubes, which serve as cladding for the fuel rods. The charging machine places more than 200 pellets into one fuel rod. Having charged the zirconium tube with pellets, the robot installs a pressure spring, pumps out the air, and seals the tube. Leak tightness of the fuel rod zirconium cladding is the second safety barrier. The fuel rod cladding is made of nuclear-grade zirconium and possesses higher corrosion resistance. It is capable of retaining its shape under temperatures of more than 1,000 degrees Celsius. Quality control over nuclear fabrication is exercised at all process stages. Multiple quality checks make probability of fuel leaks negligibly low. The third barrier is the 20-centimeter thick reactor pressure vessel, which is designed for a pressure of 160 atmospheres. The reactor pressure vessel prevents fission product releases into the shielding structure. Lastly, the fourth safety barrier comes that is the leak-tight shielding of the reactor hull, the so-called containment. The containment consists of 2 parts, inner and outer shielding. The outer shielding protects from all external impacts of both natural and man-induced origin. It is made from high-strength 80-centimeter thick concrete. The inner shielding is a concrete wall of 1 meter 20 centimeters in thickness. From inside it, it is lined with sound steel sheet of 8 millimeters in thickness and is reinforced with special systems of wires strained inside the shielding. In essence, it is a contracting steel cocoon which increases strength of concrete compression by nearly 3 times. The inner shielding can withstand a pressure of 7 kg per square centimeter and a temperature of up to 200 degrees Celsius. There is an annulus between the inner and outer shielding. It is fitted with a system to filter gases incoming from the reactor hull. The reinforced double containment retains leak tightness at an intensity 8 earthquake and a crash of up to 200-ton aircraft. It also withstands extreme external impacts, such as tornadoes and hurricanes, which are probable once in 10,000 years, and an air shock waves with a front pressure of up to 30 kilopascal. System of 4 physical barriers which constitutes the defense in-depth approach excludes radioactive releases beyond the power unit in case of an emergency. All VVER reactors include passive and active safety systems, which combination ensures meeting 3 basic goals in case of emergency: shutdown and termination of the nuclear reaction, provision of continuous heat removal from the nuclear fuel and power unit, and prevention of radionuclide releases beyond the containment in case of emergencies. In emergencies, to terminate the nuclear reaction, boron carbide scram rods are inserted into the reactor core. The rods are hanging over the core, kept by electromagnets, and drop by own weight within 2 seconds. The rods absorb neutrons and the chain reaction terminates. The second task, continuous heat removal from nuclear fuel and reactor, is solved by combinations of active and passive safety systems. A difference between them is that the passive safety system operate without electricity and involvement of personnel. Let's look at the active safety system, which is responsible for removing heat from the energy block via the second circuit. In case of an accident, if the reactor cooling circuit remains integral, the reactor is cooled by the emergency cool-down system, where heat is removed via the secondary circuit. In the steam generator, residual heat is transferred to the secondary water and then to service water through the emergency cool-down system. In case the primary circuit is damaged, high and low pressure pumps are actuated to ensure continuous water supply to cool the reactor. They supply water from the spent fuel hold-up pond located within the containment and from the containment sump. If the leak is small and high pressure is maintained in the circuit, high pressure pumps operate. If the leak is large, for instance in case of a pipeline break, and pressure is dropping, low pressure pumps are engaged. The spent fuel hold-up pond is more than 2,000 cubic meters, of which 700 cubic meters can be used for heat removal of the primary circuit. Power supply of the active safety systems is independent owing to backup diesel generators which are started automatically without human involvement in cases of power loss. Each unit with a VVER reactor includes 4 independent diesel generators located in different rooms to exclude a possible common cause of failure. Raise of pressure and temperature inside the containment is prevented by spray systems which condensate steam incoming from the non-integral reactor. The passive system ensures heat removal from the reactor core through the steam generator. It takes away steam and sends it to the heat exchanger installed outside the reactor hull. Now being cooled by outdoor air, the steam condensates and, as water, returns to the steam generator. Thereat, the steam generator is cooled and in turn cools down the primary water and, correspondingly, the core. If loss of power coincided with a break of the primary circuit, cooling water should be supplied directly to the reactor. This function is performed by a system of water tanks capable of supplying water to the reactor during a long period of time. From water tanks of the first stage, water gets in the reactor under pressure of nitrogen pumped in the upper section of the water tanks. Water tanks of the second stage supply water to the reactor owing to a difference in height at which the reactor water tanks are installed. For all that, a probability of an accident is negligibly low, and active and passive safety systems would confine it. Modern nuclear power plants are fitted also with additional safety barriers. If it is not possible to cool down the reactor core and fuel temperature rises to 2,600 degrees Celsius, the last line of defense is engaged. In this case, the reactor's pressure vessel bottom melts and remains of the nuclear fuel and reactor structures leak to the cooled refractory vessel, which is called the core melt trap. It is filled with so-called sacrifice material, which excludes a fission chain reaction and reduces the melt temperature. The trap design provides for continuous cooling of the melt with cold water and does not allow it to destroy the shielding of the reactor hull. To rule out an explosion of the hydrogen generated by the steam-zirconium interaction, passive hydrogen recombiners installed within the containment shielding are used. They accelerate the interaction of hydrogen and oxygen that results in water. With that, there is just not enough time for gas to form an explosive concentration. Special engineering features such as hydrogen recombiners, core melt trap, and passive heat removal systems are fundamental distinctions of modern VVER power units. The combination of active and passive safety systems allows maintaining guaranteed heat removal from the reactor core during 72 hours in case of a pipeline break. This time is sufficient to do required repairs. One more element of the plant safety is the principle used for selection of construction site. The site is selected by more than 20 parameters. Sites featuring karst with voids, soil collapse, and river floods are excluded. A prime focus is on seismic and tectonic features on the plant hosting region. But in spite of locating nuclear power plants in seismically safe regions, a probability of underground shocks is taken into account in design of the reinforced reactor hull. Up-to-date oil dampers in use retain strength and operability of the reactor at seismic shocks of intensity 8.